In this video, we're going to be looking at topic 3B, covalent bonding, and this is part of the IAS chemistry course from Edexcel. So you will have covered some of this content back in GCSE, but for A-level, you need to understand covalent bonding in terms of electrostatic attractions. You should be able to draw dot and cross diagrams for covalent substances. Look at giant structures of carbon atoms and identify the different types of structure and applications. Looking at the term electronegativity and understanding what it means, and how we can then apply the knowledge of electronegativity to form a continuum of bonding types going from ionic to covalent, and also distinguishing between polar bonds and polar molecules and predict whether or not a molecule is going to be polar. So in GCSE, you learn this definition, and it continues through to A-level, that a covalent bond is the electrostatic attraction between the shared pair of electrons and the nuclei of two nonmetals. So again, there's our keywords, electrostatic attraction, and we're always looking for the attraction between the positive and the negative and the compound, and in this case, it is our positive nuclei and our negative electrons. Our shared pair of electrons allow each atom to have a full outer electron shell, and we typically refer to this as the octet rule, and we will revisit this later. And the way that the orbitals are going to overlap to give us this shading is going to depend on their shape. And this goes back to when we learned about s orbitals and p orbitals. Remember that s orbitals are spherical and p orbitals have this dumbbell shape like that. Again, you should be able to draw those looking at any multiple choice question, or in an exam in a written part, they could ask you to draw out the shapes of these orbitals. So in covalent bonding, there are two types of overlap. The first is when we have an overlap on what we call end on end. That is called sigma bonds, and we can see that it's got this Greek symbol here. And specifically, we're looking at the overlap end to end for p orbitals. For s orbitals, because they are a sphere, they can only overlap in one way. But when we have the p orbitals, they can overlap one end of the dumbbell shape to the other, and we call this a sigma bond. Sometimes we can get the overlap being side to side, and we call these pi bonds, again with its Greek symbol here. And you can see that there is a difference that for a sigma bond, we get one area of overlap, whereas for a pi bond, we get two areas of overlap. Again, you may be asked to draw these in an exam, so it's important that we can distinguish between them. Now, they are still both two types of covalent bonding, because remember, a covalent bond is when we have the orbitals overlapping. They just overlap in a slightly different way. Now, when we get this pi bond being formed, this side-to-side overlap, this can only happen when we have formed a sigma bond first. So we will get a sigma bond forming and then a pi bond, and because of this, pi bonds can only exist when we have a double or triple bond. So what happens is we get the end-to-end overlap like that, and then we also get a side-to-side overlap. Now, I know that's a bit messy to see, but you can get the general idea that we have our overlap for our sigma here and our overlap for our pi there. So we get both of these overlaps happening at the same time. So in a double bond, we have one pi bond and one sigma bond. And in a triple bond, we get two pi bonds and one sigma bond. So you will always only get one set of orbitals overlapping end to end. The others will overlap side to side. We can show the formation of the bond using a diagram like this, and it can be quite tricky to follow it, so we've been able to make the orbitals different colours for you to see. So we've got our blue p orbitals and our green p orbitals, and those are the ones that are going to be involved in the pi bond. So our blue and our green. And our pink is going to be the sigma bond that forms. So we know that a sigma bond has to form end to end, so we can see that the pink is going to bond end to end here, but it's covered in our diagram so we can't see it, and the blue is going to combine side to side, and the green is going to combine side to side here, and then that forms the pi bond. So you can see that we have a pi bond being formed with the blue orbitals and a pi bond being formed by the green orbitals. So we are forming the sigma, pink, and the pi bonds between the blue and the green, giving us our overall triple bond. Now we can look at bond length and bond strength in order to give us an idea of how strong a covalent bond is. So the bond length is the distance between the nuclei of two covalently bonded atoms. So we've looked at this when we were talking about atomic radius. So if you have got two atoms with the overlap, they are going to contain a nuclei, and the distance between the two is going to be the bond length. And the strength of a covalent bond is measured by the amount of energy required to break 1 mole of the bond in the gaseous state. So again, we're looking at how much does it take to break these atoms and completely separate them so there is no longer any attraction. This is similar to how we measured the bond strength for ionic bonds, but we simply looked at removing the ions to an infinite distance. In this case, we're breaking the covalent bond to separate the atoms so they're no longer attracted. In general, the shorter the bond length, the stronger the bond, because we're getting more overlap and we're getting more increased electrostatic attractions. So the smaller the bond length, the stronger the bond. Now, a new concept that comes in at A level is known as electronegativity. And electronegativity is the ability of an atom to attract a bonding pair of electrons. Now, what this means is that if you have a bond, like between two hydrogens, the electrons are shared and they are going to sit perfectly in the centre. So there is an equal attraction for the electrons from the hydrogen on either side. And that's because they are the same atom and they have the same electronegativity, in this case a value of 2.1. Now if we were to take the hydrogen and bond it to something like chlorine, you can see that we have this value for electronegativity, and the higher the value, the more the atom will attract the electrons. So if we take chlorine, we're comparing a value of 2.1 to 3. And then what actually happens is we get our electrons moving closer to the chlorine than they are to the hydrogen. And this causes what's known as a polar bond. So we get a difference in our atoms in terms of their ability to attract the bonding pair of electrons. The chlorine prefers to pull the electrons closer to them. And we'll come back to polar bonds in just a few minutes. So what we just need to know for now is electronegativity is the ability to attract a bonding pair of electrons, and you get this table in the data book that you will be able to use in your Unit 2 and Unit 3 exam. Because you're not allowed to use the data book in Unit 1, what you do need to know are the trends in electronegativity. So electronegativity increases as you go across a period. So as you go from lithium to chlorine, the ability to attract the bonding electrons increases. And this is because you get an increase in nuclear charge. So because you get more protons, your electrons are going to be more attracted, so it's going to be pulled closer. As you go down a group, the electronegativity decreases, and this is because you're adding in quantum shells. So you're getting an additional energy level of electrons, so your outer electrons involved in bonding are further away from the nucleus. So these extra energy levels are going to shield the bonded electrons because we're going to get this electron-electron repulsion that we discussed back in topic 2. So the outer electrons involved in bonding are not as strongly attracted to the nucleus. So my electronegativity value decreases. Now, if we have this difference in electronegativity and we get the electrons being unequally shared, they form what we call a polar bond. And you can see the differences when we look at electron density maps. So if you have chlorine atoms, we know that this, obviously if it's the same atom, they're going to have the same electronegativity. So we get an equal sharing of the electrons. So our electron density maps to show where the electrons are and give us the shape of the atoms are identical. When you compare that to the hydrogen and the chlorine that we've looked at, where we have 2.1 to 3, we get this unequal sharing. And what that means is the electrons are being pulled closer towards the chlorine, so it has a larger electron density in comparison to the hydrogen. Now, polar bonds are a type of covalent bond, so they still have an overlap of the orbitals. That doesn't change in comparison to what we call a pure covalent bond. So polar is when we get the unequal sharing that we've just seen, and we call it a pure covalent bond when we get an equal sharing of the electrons. The main difference between a polar bond and a pure bond is the position of the electrons within the bond. So the electrons are always going to be pulled more towards the more electronegative atom. And what this actually does is it causes a slight difference in the charge. So if we have a pure covalent bond, the electrons are held perfectly in the centre. When we start to get this movement of electrons, so if we go back to our hydrogen and our chlorine, we said that the chlorine was going to pull the electrons closer. And what happens is it causes the chlorine to become slightly more negative. And we show this by using this delta Greek symbol and a negative sign. And if this side becomes slightly negative, the other side becomes slightly positive. And we show that by having this delta positive. So if you see a delta positive and delta negative, this tells you that there is a difference in electronegativity. And the more electronegative atom is going to be the negative charge. So for example, if we have carbon and chlorine, carbon has an electronegativity of 2.5, chlorine is 3. So the chlorine is the slightly negative, and you can see that we have this arrow here, and the arrow shows the electron movement or the attraction for the electrons, so which one they're going to be more attracted to. Hydrogen has an electronegativity of 2.1 and oxygen has 3.5. So the oxygen is the slightly negative, the hydrogen is the slightly positive. Again, hydrogen 2.1, nitrogen is 3, so they're going to be towards the nitrogen. And comparing to carbon, carbon is just ever so slightly more electronegative, but it will still attract the electrons more compared to the hydrogen. Now we can use this concept of polar bonds to tell us the different types of bonding and how we can start to build a continuum. The two ideals of bonding are pure covalent and pure ionic. And the polar covalent bonds make up this part in the centre. So eventually what happens is we have a pure covalent bond where we have no difference in electronegativity. A polar covalent bond, we start to get this pull of electrons towards one of the atoms in the bond, and eventually the difference in electronegativity is large enough that the electrons will actually transfer between the atoms instead of being shared, and we then transition to an ionic bond. So a polar covalent bond is still a covalent bond, but it has some what we call ionic character. And it is because we start to have this unequal sharing of electrons and eventually leading to electron transfer. By looking at this equal and unequal sharing and eventually transfer of electrons, we can start to build what we call the bonding continuum. And this just shows how the difference in electronegativity leads from pure covalent all the way through to ionic. So when we have zero electronegativity difference, we get our pure covalent, and this means that we get our equal sharing of electrons. And we're looking at this in terms of percentage of approximate ionic character. So if we have equal sharing, we have no ionic character. They are perfectly covalent. As we start to increase the electronegativity difference, you can see that the percentage of ionic character starts to increase. And these then become our polar bonds. But we still class them as polar covalent. And this is our unequal sharing. Now, there's no particular cut-off point where we say this is definitely ionic at this point. What you would do to determine that is you would look at the elements involved. But once you start to get above electronegativity differences of about 2.5, this is only going to be possible when we have metals and non-metals. And we start to get to the point where we have ionic bonds, and this gives us the transfer of electrons. So we're not looking at any shading anymore, we're starting to see a full transfer of the electrons. And this is our bonding continuum. So we go from our pure covalent, we increase the electronegativity difference to form our polar covalent, and eventually increase it so much where we get a transfer, and now we start to see ionic bonds. Now, when we're looking at covalent bonds, we can then discuss what's known as discrete covalent bonding. And this is what you would have covered last year as covalent molecular bonding. Discrete just means individual, or sometimes it's called simple molecular. And these are an electrically neutral group of two or more atoms held together by covalent bonds. In other words, these are small molecules that have no charge overall, and they are made up of covalent bonds. For example, water, methane, ammonia. These are all discrete covalent molecules, and we can draw them using dot and cross diagrams, and you've seen this back in GCSE. If you can't remember how to do this, I'd recommend you go back and practice some of these using GCSE textbooks, or there are some practice questions in the A-level textbook as well. Notice again, we're being very specific here about the dots and the crosses to show which electrons are coming from which atom. Now, at GCSE, you learned that all atoms want to have the same number of outer electrons, which is 8, looking at a noble gas, and we called this the octet rule. Now, whilst this is the case for the majority of substances, it is not always the case. There are some elements that contain less than 8, and there are some elements that contain more than 8 electrons in their outer shell. And these are just some exceptions that you have to know about, and we'll discuss these further in topic 3C when we are looking at the shapes. Now, be aware that the majority of molecules will want to conform to the octet rule, but we just have to be aware of the few exceptions. So 4 exceptions are beryllium chloride, or BeCl2, only has 4 electrons around the central atom rather than 8. And that's because beryllium itself only has 2 unpaired electrons, so it can only form 2 bonds. Boron trichloride, or BeCl3, has 6 electrons, again because boron only has 3 unpaired electrons, so it can only form 3 bonds. Phosphorus 5 chloride, or PCl5, has 10 electrons around its central atom. Now, you've normally seen the phosphorus with 1 lone pair and 3 bonding pairs, or 3 electrons that are able to bond. What happens in PCl5 is that lone pair of electrons that would normally sit like that, they separate and form 2 electrons that can each bond to something else. And for sulfur hexafluoride, or SF6, it has 12, because again, it does the same thing that you normally would see it drawn like that, and the top and the bottom pairs of electrons split and they become individual, allowing the sulfur to form 6 possible bonds. Now again, we will come back to these when we're discussing the shapes of molecules, and you don't need to know why the electrons split up from their pairs and form bonds, you just simply need to know that they do. Now we can also show multiple bonds, such as double or triple bonds, using dot and cross diagrams. And the most common ones that you'll have met are oxygen with its double bond, nitrogen with its triple bond, or carbon dioxide with its double bond. And we can show either the dot and cross, or we can show the full displayed formula showing our bonds as our lines to show the bonding pair between the 2 atoms. Again, you covered all this in GCSE. If you can't remember how to do it, I suggest that you practice and go over this. Again, there are some questions in the textbook, or check back in the IGCSE book. Now there is a new type of covalent bond that you have not met before, and this is known as a dative covalent bond. And a dative covalent bond is formed when the empty orbital of one atom overlaps with an orbital containing a lone pair or a non-bonding pair of another atom. So we've got an orbital that has no electrons overlapping with an orbital that contains 2 electrons. For example, if you have a hydrogen ion that contains no electrons at all, it has the 1s orbital, and that 1s orbital in a hydrogen ion is empty. So that 1s orbital can overlap with an ammonia molecule that contains this pair of electrons that are already paired up, so we call this a lone pair or a non-bonding pair, and that donates both of the electrons from the ammonia into the hydrogen ion, causing a bond to be formed. And this bond here is our dative covalent bond. So rather than the electrons coming from 2 separate atoms, they are shared, but they come from the same atom. So if you have a normal covalent bond, your dot and cross diagram will have that to show a covalent bond, to show they're from 2 different atoms. When we have a dative bond, we should show both of them as crosses so that we can see that it comes from the same atom. Now, in a dative covalent bond, the bond is shown by an arrow from the atom providing the lone pair to the atom with the empty orbital. And the overall substance, when we have this dative covalent bond, becomes positively charged, because we end up with a molecule with a central atom that has more bonds than it should. For example, if we look at the hydroxonium ion, or H3O+, we have a dative bond between the oxygen and one of the lone pairs to the hydrogen. So we draw our arrow going from the oxygen to the hydrogen. Now, oxygen should normally only have 2 bonds. Now it has 3. So this overall substance becomes positively charged. When we have it happening with the ammonia, we form the ammonium ion. So you met ammonium and the hydroxonium at GCSE, but you were always told don't worry about the structures. Well, now you can explain the structures by stating that we have a dative bond forming so that the oxygen and the nitrogen donate 2 electrons to the hydrogen ion to form this dative covalent bond. Again, notice that we're using 2 crosses to show that the electrons come from the same place. Another example of dative covalent bonding is seen in aluminium chloride, which is surprising because you would assume aluminium chloride is ionic, but because we have a level of polarization, we can get the aluminium chloride having some slight covalent character. Now, don't worry about explaining why that is the case. All you need to know at this point is that aluminium chloride has dative bonds. So the aluminium has 3 electrons in its outer shell. And those 3 electrons then bond with the chlorine to give you 6 electrons in the aluminium chloride. Now, just above its sublimation temperature, in the gas phase, aluminium chloride actually exists as 2 of the AlCl3s joined together. And we call this a dimer. And I'm going to show you what this looks like. So one of the atomic orbitals of a chlorine overlaps with the empty orbital of the aluminium. Remember that each of the aluminiums are going to be, each of the 3 electrons in aluminium are going to be bonded, but we know that the third shell can hold 8 electrons when we're looking at the p orbitals and the s orbitals. So we have an orbital that doesn't have any electrons because we only have 6. So that empty orbital can overlap with a lone pair on the chlorine and we form a dative bond. And we can see that here. So this lone pair overlaps with the aluminium, empty orbital, forming a dative bond. And then the same thing happens with the other chlorine and aluminium, bonding these 2 units together to form this dimer. So we have the AlCl3 bonding with another AlCl3, making 2 different dative bonds, holding the molecule together, and we form a dimer of Al2Cl6. This can come up in an exam, and you could be asked to draw this. Just always make sure that you draw the arrows going the correct way, going from the lone pair of the chlorine to the empty orbital of the aluminium. We're going to finish off by looking at some past paper questions. So this is from the January 2019 paper. We're looking at the electrostatic attractions involved in a covalent bond, and they are electron-electron, nucleus-nucleus, and electron-nucleus. And we want to think about what's being attracted and what's being repelled. So if we have electron-electron, we know that the electrons are negative and the electrons are negative. So that's going to be a repulsion. So we can automatically discount A and C. We know that they can't possibly be correct because we have to have a repulsion between 2 substances that have the same charge. Then we want to think of the nucleus. Well, both of the nucleus are going to be positive. So again, this must be a repulsion. So then we look between B and D. It's telling us that one is repulsion and one is attraction. Well, it can't then possibly be D because the nucleus and nucleus are not going to attract. So by process of elimination, without even looking at the electron-nucleus attractions, we know that the answer has to be B. But let's just double check that when we have an electron nucleus, we have the positive nucleus and the negative electron. They are going to have an attraction, and that's our answer that we have here. So the answer to the multiple choice is B. We then want to think about chlorine and the bonds that it forms in its chemical compound, and it can form a covalent bond with hydrogen. So the first question asks us to give the electronic configuration of chlorine using our SPD notation. So the atomic number of chlorine is 17, so it contains 17 electrons. So we know that it is going to fill the 1s first, followed by the 2s, and then the 2p with 6. So now we're at 10 electrons. So now we move up to the 3s with 2, and then the 3p, well, we are at 2, 4, 10, 12. So we have 5 electrons in the 3p orbital. And then we want to draw a dot and cross diagram of hydrogen chloride showing the outer electrons only. So we're going to have the chlorine with 1, 2, 3, 4, 5, 6, 7. and it overlaps with the hydrogen, and the hydrogen contains one electron, which I'm going to draw as the dot. So I have now got 2, 4, 6, 8 in the outer shell for the chlorine, and the hydrogen, it only wants to fill the 1s, so it has 2, so that's your dot and cross diagram. And then for 3 marks, describe fully the formation of the covalent bond in the hydrogen chloride in terms of the orbital overlap. So the first thing we want to do is we want to think about what orbitals are involved. So in the hydrogen, we have a half filled 1s orbital. And in the chlorine, we have a half filled 3p orbital. Remember, the orbital is the space that holds just the 2 electrons, so if each of these have 1 already, they are already half filled. We then get an overlap of end to end to form a sigma bond. And for a question like this, I would always recommend draw a diagram. You can easily pick up marks for a diagram. So we can have the s orbital overlapping with the p orbital, and there's our area of overlap. And that gives you your 3 marks. So you've got the half-filled 1s, the half-filled 3p overlapping to form a sigma bond. So you can see there's the mark scheme for the first questions, and then the mark scheme for the last one. There are 4 possible points. So we got mark point 1, mark point 2, and mark point 3. And you can also see that you get a region of high electron density, just referring to the point of overlap. But you only need to say 3 out of the 4 points. That's everything for topic 3b, covalent molecules. Again, I would strongly recommend that you practice your dot and cross diagrams and you practice how to draw out the different areas of overlap and sigma and pi bonds. Please check the textbook for practice questions as well as past papers. If you have any questions about this video or the content in it, please feel free to leave a comment below, and we hope to see you back soon.